Hello, everyone. Sorry I was muted without noticing it. Cool. Think I can start while allowing some people to join the very last minute. There are some places in the front if you want to come in the front. There are some places here. So let's kick this out. I'm already 1 minute late. So hello, everyone. In this 40-minute-ish or so, we're going to talk about machine learning with a language that is my favorite, but it's not the one of the third option that you think of when you think about machine learning and artificial intelligence and such. A quick intro and the boring part. Let's get rid of it. I'm Mohammed. I work at audio streaming company Spotify, and also I'm Google developer expert for Google Cloud, and I'm Java developer, so I'm backend engineer mostly with using Java, hence the talk today. Disclaimer, I'm a backend engineer, as clearly mentioned there, so if you're a machine learning expert, I'll learn from you more than you're going to learn from the session today. But this is basically the journey that I had to take in order to play a little bit with machine learning and experiment with Java and see how far we got compared to a couple of years back. But yeah, moving on. So I'm originally from Morocco, and I moved to Sweden almost 3 years back. And whoever moved to another country, it's a big step to take, mainly because it's different culture, different environment, different weather, you guessed probably. And also, it's a new language to learn in order to be immersed into this new country, learn about what's happening in there. Language is definitely something you want to learn, you want to understand in order to politics and immigration policy and all what goes with moving to a new country. And Benny had actually a good book in how he managed to crack a lot of languages. He can speak dozens of languages, and he can do that, or he shared his experience with how he managed to do that in a little bit over 3 months, which is quite impressive if you think about it. So Benny's strategy is very different or quite controversial to the way we learn a language, basically. So in a typical language, what we do is we start by learning the structure of the language, meaning that we start by having learning some words and trying how we can structure a good sentence, just like the subject, the verb, and whatever goes after that. And we start to build that patterns by learning the rules first. What Benny suggests is actually quite different. He just goes there and immerses himself with start speaking the language with whatever words he knows already, and then that will allow him to build the patterns. So he's gonna make a lot of mistakes in the beginning. It's more of a trial and error kind of mindset. And then he will try to reverse engineer the rules and then build the patterns out of the language. And that's how he managed to crack the language in 3 months. That's kind of the TLDR from the book. And if you think about it from a software engineer perspective, what we're trying to do is actually more of the traditional way of building or making the computers actually smart. So let's think a problem, because in software engineering what we do is actually solving a problem and modeling the world behind us, and modeling the problems that a product manager or a product came with, and we try to solve that by writing a set of rules. And let's try to model walking, basically. So we try to come up with how we can model the walking requirement in the constraints that we have. And we come up with this unit of measurement, which is speed. And we say that if the unit of measurement, speed in that case, is less than 4, we consider the person as walking, right? And then, there is no software that stays the same forever. Product manager came in a few weeks afterwards, and he says, oh, we need to model running. in order to model running, you say, that's not a big issue. We can just unit the same unit of measurement, which is speed, and then say, if the speed is less than 4, it's still walking, otherwise we consider everything as running. And then product manager came in with a third requirement in which we need to model cycling. And cycling is quite different. So you made more changes into the code and making sure that if the speed is less than 12, then you consider it running. Other than that, you consider it as cycling. Now, in all those requirements, we kept using the same unit of measure, which is speed. But what happens if we start trying to model a new thing, which is golfing? So golfing, you do it standstill. So there is no unit of measurement speed there. So what you need to do is that's what we call refactoring. So you rewrite the whole system, trying to introduce a new unit of measurements in order to model that requirement. And that's how we historically try to make the machines smart. So traditional programming, it's a way to make the machine or the machine smarter. And what we do is we write a set of rules and try a bit of data, shove that into our program, and that's what we call program. And then we end up with answers. So we try to model the world by writing a set of rules and trying with some data, and then we ended up with getting answers, and the answers is actually what the program execution and the behavior of the program. And if the rules are wrong, that's what we call bugs. So bugs is actually an error if the rules that we wrote, either the rules or the data, and then we try to figure that out to regenerate the results that we are expecting and the answers that we are expecting. And that's one way of making the machines actually smart and do the way that we want them to do. Machine learning or artificial intelligence, what try to do is actually taking the other way of working, or the other perspective, which is instead of writing the rules, we let the machine actually figures out the rules by itself, and we do that by changing the input format. Instead of giving it the rules, we give it the answer, which is the output and the input, and we let the machine try to figures out the best way to model the requirements that we are trying to have and what we're trying to build. And at the end, through a lot of statistical models, statistical mathematical equations and rules, we end up by building the rules and the program in order to match the best guess and the best answer that we have. So that's how I like to think about machine learning and artificial intelligence from a programming point of view. It's similar to what we have been doing, but instead of us as programmers writing our rules engine, the rules engine are actually figured out by the machine through a set of statistical models. And that's basically it. I thought it's probably I would look smarter if I put that text in there, but it says exactly what I mentioned earlier. So we just give the data and the output, and we let the machine actually figures out how it can best model the word we gave it in, or the problem we gave it out. And there are quite different practices or domains when we talk about artificial intelligence, machine learning, and deep learning. Pop science magazines try to use them interchangeably because they are very related and comes from within the same family. But there's quite some fundamental differences between a few of them. Artificial intelligence go back to the 50s, where a group of scientists and software engineers tried to mimic human behaviors and make the machines actually smart. So we came up with a lot of experiments, a lot of resources, a lot of algorithms in order to mimic that behavior. And we managed to build some robust artificial intelligence models, such as the one that plays chess and have beaten all the world champions for chess. But that's very specific to the domains and can't deal with fuzzy problems such as classification and regressions and image classification and you name it. So we needed some other way in order to deal with those fuzzy, more generic problems. And that's when machine learning comes in. The machine learning is a subfield of artificial intelligence. Oh, that was hard. Artificial intelligence, and one of the most successful ones, actually. So machine learning it deals with basically statistical models. However, it's quite different from thinking as pure mathematics. So it differs from math and statistics the same way medicine differs from chemistry, because medicine deals with its own set of challenges, even if it's a subset of it, and they are fundamentally kind of the same. Machine learning differs from statistics and mathematics in a way that it deals with large data that traditional mathematics and fundamental mathematics doesn't have to deal necessarily with. So in machine learning, we have less math, less statistics compared to fundamental math. However, we deal with large and huge amount of data, terabytes of data, and even beyond that in order to build the model that we need. And deep learning is actually a subset of machine learning, and where we went a couple of steps further and we said, instead of having this one representation of the model, let's actually try to combine those representations. So deep learning is basically combining and condensing the representation to build a model, a more kind of smarter and capable model. And then you probably already, I think the session before was about generative AI and LLMs. And there is a huge hype now around generative AI and LLMs and what they can do and what they are capable of. But it's a subset of deep learning. AI, machine learning, and deep learning try to give the same answer, to build rules to give the same answer that we trained them with. Generative AI actually try to generate new things rather than giving the same answer. So that's how it's fundamentally different than the previous traditional models or traditional algorithms. Is try to generate things. And when we talk about hallucination, which is the $1 billion question now in LLMs and generative AI, it's actually not a bug. It's actually a feature, because we trained those AI, we trained those Gen AI stuff in order to come up with those new creative words, images, whatever, and that's what they do. And creativity can sometimes be misleading. Okay, moving on. Yeah, I mentioned that before. So deep learning is actually taking machine learning a little bit further and having a lot of different deep representation and different layers of representation. So the deep in deep learning is actually the depth of the is actually how deep and how much layers we have, rather than the depth of the learning. So we put a lot of layers and we try to extract each some of information, a lot of information from the input layer. We represent it in the different formats, and then each layer has different representation, and then the final model will basically condense all those information into the output layer. And that's only possible because we have now computing power. That wasn't possible before because we had limited resources. Now we are capable of having hundreds of millions of layers, hundreds of millions, wow, that's so much. Hundreds of layers combined in order to have multiple representation of the input, and then have an output that's basically a condensed view and a much rich view of the original model, and predict the data that were coming in. Yeah, and then machine learning and artificial intelligence, or machine learning precisely, is pretty much everywhere. We use it in the shop, on the e-commerce software that we use. It's our mobile, it's on our tagging algorithm, from our image tagging algorithm in our phone. It's pretty much anywhere. Smart assistants, speakers as well. It's become a fundamental part of our life in the recent years. However, when it comes to learning it and trying to interact with it for a lot of years, the moment you want to enter that realm of machine learning and artificial intelligence, you were like bombarded with a lot of with a lot of words: gradient descent, vectors, linear algebra, and Python as well. So all the demos, all the tutorials were using Python. Python is a great language. It does the job, and it does it very well for data science and machine learning. However, I'm a Java developer, so I don't want to learn math because I'm not passionate about it. And I don't want to use Python for a daily basis. I can use it for ad hoc when I need it, but I'm a Java developer and I want to integrate machine learning algorithms to build something out of it because I'm a Java engineer and I use Java on a daily basis. And as it turns out, a lot of Java developers share the same frustration and share the same feeling. And Humphrey wrote a very good article a few years back in 2018, basically saying what fundamental changes or what changes the Java language needs in order to make it more machine learning friendly. And Java and ML actually makes a lot of sense because like Java is one of the either first or second programming language, the most popular one, highly used. It's really scalable, very performance using in mission critical applications, enable us to go to the moon. It has a great community. This conference couldn't have been possible without the Java community that has all over the world, enabling us to connect, share knowledge, and get knowledge as well, and meet other friends. And Java historically has multi-device support from mobile to servers, you name it. So Java is pretty much everywhere, and it makes sense probably to have support for more or better support for machine learning in Java. So the rest of the talk is going to be basically exploring some of the libraries, frameworks, tools that we can use nowadays in order to basically start interaction with machine learning in Java. So I'll start first by talking about JSR 381, which is Java specification request specializing in image recognition. And then I'll go to talk about deep learning for Java, the deep learning for Java from Eclipse Foundation, deep Java library from Amazon or AWS, and then Tribuo from Oracle. Okay, first things first. JSR 381. That's an initiative that a few Java community folks came with, and it was an initiative to make interaction with Java and ML and make it a lot more Java friendly, a lot more easier. And it's very specialized on neural networks in deep learning, and also the first iteration is focusing on visual recognition, basically. So the algorithms that are there supports handling images. And it's basically, as any JSR, it has a reference implementation, and the reference implementation is DeepNets. And the other implementation is GDL, Java Deep Library from AWS, which is an implementation for this JSR as well. Let's have a quick look at how easy and beautiful deep Java, okay, it's Vistrik, is this one. Before that, probably a context would help. How many of you have watched the Silicon Valley? A few hands. Okay, so for those who watched it, you remember the hot dog or not hot dog application. That was super fun. But for the rest is basically this guy or one of the engineers built an application that basically take a picture of the food or picture of whatever and says if it's a hot dog or a not hot dog. And that was quite literally. If it's a hot dog, it says it's a hot dog. If it's not a hot dog, it basically says not a hot dog. So if have an image of a pizza or something, just say it's not a hot dog. So the enthusiasm was there, but the delivery was not there. Nevertheless, so what we're going to do is basically build something similar in 2024 with Visric, just because the model is easy now to build, and also it's going to be quite fun. So what do we have here? So I'm using GSR 381 Visric with the reference implementation from DeepNets. So we start by declaring our neural network, or specifying our neural network. It's a neural network classifier, and since we are dealing with images, it's a neural net image network classifier, obviously. We are expecting an image classifier as the output, and we are feeding it with buffered images, right? So the input class is buffered image. We are mentioning the width and height of the images, 128. We are specifying the labels path. Labels are basically, where is it? Labels, it's under resources, Visric, it should be here, labels, yeah. Oh, yeah. Labels are basically it's the output layer, what we are trying to predict. Is a hot dog or not a hot dog? And then the training file, and that's all the data that we're training our model with. It's index.txt, it should be this one. And what we're doing here is we're specifying the path of the image to load it and then to tag it, and we're having a tag here. So that's the input layer that we are giving it, basically. So this image is not a hot dog, and then those three are a hot dog, and then the data is basically here. So I have a data set with test and train. Training is the training data, and then I have a few images of hot dog, such an ugly hot dog here, and then we're having images of not a hot dog, and okay, whatever. Sorry, Mar. At least it's not a pizza. Okay. And then we are building, so we're mentioning the labels file, we're mentioning the training file, and then we are having a neural network architecture, which is the architecture of our network. And that's basically our deep learning model and the layers that we are defining in order to train our model. And that's defined in a JSON file in here. And that's what I very much like about Visric. It's, as you can see here, it's followed convention over configuration. Everything is externalized in a config file, makes it easier to use, very less verbose, or it's very compact. It's less verbose than we think about generally about Java, which is really cool. And then we have here our, no, I wanted the JSON file, this one. So we're defining our convolutional neural network. It's basically a type of neural networks that is very widely used when it comes to handling images. And then we're defining how many inputs, 3 channels because we're dealing with colors, RGB. And then we're defining our, maybe that's too big, and defining our layers. So the first one is, so that's the input. Then we're adding another layer, it's convolutional, having it more channels here, so more inputs, 6. Then max pooling to condense the layer, and then fully connected, and then we're having an output layer with basically one output, which is if a hot dog, otherwise it's not a hot dog. So in a production level, production grade neural network, you would end up with dozens of those layers defined, basically, or even hundreds. But for the sake of this presentation and this demo, it's easier because I trained this model basically on my machine, which is an M1 machine, so it's a lot easier to work with. And then we have a few configurations in here. So we're defining the max error. So if while training our model, if the max error exceeded 3%, just gave up, and then the maximum number of train iterations, how much you would train, and the learning rate, it's also 1%. So you would tweak those numbers based on your need, and then export the model. When we train our model, the final format or the final model, save it into this file called hotdog.dnet, and dnet stands for deepnets basically. So I already run this, took a couple of minutes, a little bit more than that, and then I have my file here. And then for the inference, which is basically embedding this in your Java application as well, it's quite simple. So I just load the file, which is a convolutional neural network, and then I invoke an image classifier, and then I feed it with an input just to run the inference, run to the prediction. So I have a image pizza here, super fun pizza. Sorry, Mario. And then I have a hot dog pizza in here, very ugly pizza as well. But yeah, you get it. And then let me try to hot dog dish. Okay. And then it loads the image, it runs the classifier, and then the prediction or precision here is 50%, so 0.5. If it's more than 50%, it's a hot dog. If not, it's not a hot dog. But you probably won't want to have more than that if for your production application, but that's just for fun here, right? And then if I run this one, I hopefully should have, okay, this is likely to be a hot dog, right? And then if I run the pizza image, okay, it's definitely not going to say this is a pizza. It's going to say this is not a hot dog. So that's pretty much it. It's quite easy to work with, especially if for small applications. Download it. Check other models, build it, and then use it. And what I like, as I mentioned before, is like quite compact compared to what you expect from Java. But as I mentioned, VisRec is very focused on image recognition. So it deals a lot with images and other algorithms. Neural networks models will be coming up next, hopefully. The second framework is deep learning for Java. And deep learning for Java was, Deep Learning 4G was one of the first and the oldest Java frameworks that aims to run machine learning into your Java applications. So they basically ended up building everything from the ground up. And we have a couple of components there. Deep Learning 4G, the layer above, which is the framework and all the APIs that we deal with and invoke from our Java application, either to train the model or to embed it and load the model and run the inference, right? And then we have another fundamental building block, which is the ND4G. And then the ND4G is a linear algebra library, and it basically does all the computations, all the calculations, and it runs and train your models. It supports both CPU and GPU thanks to libND4G. So libND4G is basically a C++ engine that enables to switch either to CPU or GPU if actually needed. And ND4G also supports running distributed training with Spark, which is really cool. And they ended up building the whole thing because they wanted to be offering a more powerful set of tools, more autonomous for both programmers and researchers that want to build and experiment with machine learning models and algorithms. Some of the features of Deep Learning 4G is it supports all major type of neural networks: convolutional neural network, feedback or feed-further neural network, RNN, LSN, LSTM, GANs, all major architectures of neural networks. It also supports import or export of other models such as PyTorch, TensorFlow, and Keras. So if you used one of these, you can export the models or import it depending on where you generated the model. Deep Learning 4G, from an architecture point of view, if you used ever Keras or have a knowledge of it, it's very influenced by Keras. So the model and the way of thinking is very similar to Keras. But Keras is very cool, very powerful, and very developer friendly, especially machine learning ones. And then I spoke about ND4G. It's kind of the backbone of the computational power of Deep Learning 4G. It has distributed training capabilities. It can switch between CPU and GPU. Deep Learning 4G has also what we call models.We, and models.We is kind of pre-trained, ready, available to use models that you can just load and start using from day zero. So they provide that as well, and it has multi-language support, so we can use Scala and Java as well, and Python. Why would you use Python? Anyway, but yeah, it mentioned that. So some of the use cases, probably we can check a quick demo about it as well. So deep learning for Java, no, this one. You can see that I'm scoring more, and that's intentional because deep learning for J wants to offer you more tools in order to fine-tune and build your own model, which not everyone needs basically, but this is the decision that they have taken, and then this is what we ended up with. So the file is longer and it has a lot of blocks. So here we're just setting up the data, defining our test path, training path, and then the number of labels. And it has a lot of, like small features or small capabilities like this one. So from the directories, it can read basically and get the labels. So it has a lot of utilities that can help with that. And then we are defining our neural network model. As you can see here, what was in JSON on the other file is actually defined in Java API in here. So we're defining our seed, learning rate, and then the optimizer, updater, those all kind of some of the metadata that you provide to your neural network in order to train it. And then here's where we define our layers basically. So we start with convolutional neural network and then a sampling layer, another convolutional neural network and sampling layer, similar to what we have previously, but now it's more from a Java layer. And then we end up with our output layer basically. So we define our neural network here, and then we start our training, not here. This is more of UI server. A UI server is a way, so a web application that can integrate with while training your model in deep learning 4G. It's basically give you a visualization of how your training is basically going. It's really useful if you are doing multi-node training and distributed training for your nodes. And then we're loading the data, splitting up the path, doing some optimization with the files, and setting the listener that basically goes to the UI server, and then we're training the model here. So we have a number of epochs, which is I think 1,000. We set it up previously, and then we iterate over train our algorithms, and then it fits based off. It improves the learning. If the error is out, it's go again, and so on and so forth. And then we end up with evaluating the data from our test data sets, and it check how good our algorithm is basically and then we save it in somewhere, similar to what we did previously in a file called hotdog.bin. And then to use it is no, not this one. Okay, so that's inference. But to use it should be similar to what we did before. So we get the, is it here? No, it's here. Should be similar to what we did before. We load it, and then we use it to run the inference basically. So that's one way of doing it, defining your own neural network. Generally, that's not what we do. What we do is we can use a pre-existing, predefined, pre-tuned model available there, and then you add your layer, your final layer, in order to tweak it to tune it to your own needs basically. And what we are having here is I'm using the, sorry for that, I'm using the, okay, if I can find it. This first part is exactly the same, nothing much, but what I'm doing here is doing what we call a transfer learning. Transfer learning is basically using a model that is already predefined. In this case, is ResNet 50, which is a image classification model based on neural networks. And then what we add another layer on top of that, basically, in order to tune it to what we need. And here, in this case, train it to tag only hot dog or not hot dog. And then it saves the outputs and stuff. Thanks, Mario. So yeah, that's pretty much it for deep learning 4G. TLDR, it comes, what? Where is my, yeah. It comes with more, it offers more features, it comes with more power, but it's very verbose, but it's really useful if you want to build your own neural network model. Use cases, I'm not sure if I mentioned that before, but it's used for image classification, same as the demo we did. Convolutional neural network can be used for medical imaging, agriculture, and stuff. Natural language processing, building your smart assistants, text to speech, speech to text, those kinds of stuff. Such chatbots, even now. Natural language processing looks a little bit dumb compared to generative AI. And then gaming and robotics, one of the fields that it can be used a lot, deep learning for Java. But it has a steep learning curve because you need to tweak everything. Similar to machine learning, but with deep learning 4G it becomes more obvious because you need to tweak everything. Even the smallest thing needs to know why and the configuration and stuff. So it has a more steeper curve compared to others and lacks of high level abstraction. So everything needs to be manually set in the APIs. And it's lately has a slow release cycle. It feels kind of not being highly or actively maintained nowadays. Probably just my feeling, but it feels like it has the release cycle slowed down lately. Okay, second one or third one, my favorite one, Deep Java Library. Deep Java Library took a different approach. So rather than building your own engine and the backend implementation of it, they basically build an agnostic layer, agnostic framework, which is DGL with Java API. And then they built an interface, a lot of interfaces that can interact with, that can invoke different engines, such as PyTorch, TensorFlow, Omnix, OnNex. And then they wrote specific implementation and specific lines for each and every one of them. So they are not building their own framework for running data or running training and stuff. They are reusing basically the well-known frameworks that we already know in the Python world, and they are building basically a tiny little Java library on top of it. So it basically benefits from all the advancement of those frameworks that was already offered, which is really cool. So it has multi-framework support, which is really dope. It has TensorFlow, PyTorch, MXNet, and others. I find that super powerful because like TensorFlow and PyTorch are, and along with Keras, are the one mostly used in this, at least in the machine learning world. So having interaction with them with the Java API is really good. It has a very cool deployment model. And what I did here is, okay, Docker PS, if I manage to type Docker correctly. Okay, now I can. So basically, a simplified deployment model, either do it on your own, or they have a pre-made web server, which is, I'm running a container here. And if you go here, it's basically you can find the DGL server. So this one is the application that they built. Very simple application. You can add your model that they support either from PyTorch or TensorFlow and the ones we mentioned, and then you click submit and it will be basically there. So I already did that, and I have AresNet. So remember the one that we mentioned in deep learning for Java. So AresNet is kind of image classifier. You give an image, it gives you a list of tags. So what I did is, as I mentioned before, went there, added the URL, click submit, and then it went there. And then I have an Insomnia client. Basically, so everything, all the models will go under production, and then you have the model prefix, which is ResNet 18. And then what I want to do is give it an image. I can remove this one. If I want to change it, so I have a lot of, okay, let's try this one. See how if it will be able to detect if it's mouse or not, or what image tags it would return. It takes some time, because like it would return, my image is not powerful enough, but hopefully we should get something really soon. And I'm running out of words. Hello? Yes. So it's managed to figure out a hamster, word rabbit, blah, blah, blah. So just to say that you can easily start integrating machine learning in your Java application from now. So there are already a lot of pre-made models that can pretty much do some of the stuff that you probably need, or add some tweaking, and then it's basically it. I'm not sure if you can see, but with that, you can, if you have, for example, a user uploaded image, you can easily use ResNet, tag the images, and then if any sensitive content in there, you can easily block it without being a machine learning expert. So one of the use cases that you can use out of the box with having zero knowledge about machine learning. That's how easy it became nowadays, and that's the message that I want you to get from this presentation, basically. So yeah, pretty easily. It has a REST API. You can integrate with it, integrate it with your pipeline pretty easily. Okay, so I was in the simplified model. It has a very rich model zoo. ResNet was part of the model zoo that they provide, but they have a long list. The richer that I found in the Java libraries that I've mentioned. It had a simplified model deployment. I think that's redundant. Model server, the one I mentioned, and yeah, a few other things. Use cases, as any deep learning library: image recognition, natural language processing, similar to what way I mentioned. Time series analysis, detecting anomalies, signal processing, recommendation system, music, what's called e-commerce, you name it. Fraud detection. If you have like transactions, it can detect that. Robotics and security stuff. But model compatibility could be an issue because they don't have their own engine. They basically support a lot. Okay, I'm running off. I thought it's okay. I thought it's anyway. Sorry, Mario. Because they don't have their own engine, they support multiple. It can be an issue to basically when TensorFlow comes with a new version, it can have some breaking support. The final one, I'm out of time, so I probably need to run a little bit faster. Tribuo is a traditional machine learning framework. It does only machine learning. It doesn't deal with deep learning. It's very enterprise-oriented, and it's the one that powers Oracle Cloud machine learnings, or at least part of it. So it offers a lot of enterprise features. So they have their data source plugin in there that can basically be plugged in with whatever text, image, you name it, you have, CSV, your own database, text files, whatever. So they have the data source, you plug it in, and then it takes your data source and then make it compatible with this to Tribuo compatible format. So the dataset is Tribuo compatible format, and then you can add some metadata in there, some hyperparameters, and then it runs your model and generates it, and then you can run predictions out of it. So it's very enterprise friendly. If you have a set of a database, list of files that you want to make predictions out of it, Tribuo is the way to go. But it doesn't handle more recent deep learning models. It's very focusing on machine learning models. And then some of the key features. It has diverse machine learning algorithms, traditional one, regression, classification, and so on and so forth. Data processing, it has a rich data processing support, basically because of the enterprise world needs a lot of inputs and to format those inputs before it goes to its data sets. You can evaluate the metrics because enterprise world again needs dashboards on how to evaluate and so on and so forth. Data pipelines go again to data processing, and it's kind of scalable. It's cloud friendly. Use cases: traditional machine learning model, classification, regressions, anomaly detections, and then yeah, those are very classic when it comes to machine learning. However, it's not as extensive as the other two because it's fairly new. It has less extensive models though as well. It has no interoperability with Java, non-Java ecosystem. It's very Java focused, and it has smaller community because again, it's fairly new. But it's, if you're an enterprise world dealing with mostly text, it's going to help a lot to integrate with it. When to use which? I found DGL super easy to work with, super easy to integrate. It's the community is alive there. Deep Learning 4G, if you want to more control over what you are building, more tweaking, building your own, that could be something. But if you just want traditional machine learning models in enterprise world, Tribuo could be the good fit for you. That should say that there are a lot of steps that goes from building or to getting the data to train your model until deploying it into final stage. And nowadays, we can have a full end-to-end Java flow that can run Java-powered applications, which is super cool. Thank you very much. I'm already out of time, but I'm happy to take your questions. Thank you.